got it in there partway, I'm just drawing it again.
Sorry, there's nothing I did, you pick it all
Well, figured while they're finishing the lab.
up. All right, so sort of recapping where we left off. This is what we did on Monday over here. Again, we were dealing with AC circuits. So if I just have a resistor in there, we eventually got down to the fact that my current equation was cosine, just like my voltage equation was. So they are in phase. The fact that the same function describing them both, the magnitudes are different. And so the largest value of the current right here is what I'm labeling as capital I sub R, the typical convention is the capital letter is the maximum value and the lowercase letter is the instantaneous value. So this is equal to the current, and from that, I know that the voltage across the resistor, or the maximum voltage across the resistor is equal to the maximum current across the resistor times the resistance. That looks a whole lot like Ohm's law. And so that was all summed up in this. The current across the resistor is in phase with the voltage across the resistor, and then using the maximum values, our Ohm's law version for maximum values. We then went to the capacitor one, same voltage of epsilon. I think before on Monday I did epsilon sub 0. I did something similar on Tuesday with the 252 class, and I used epsilon sub 0, and afterwards the student came up and asked, why is permittivity in there? And so I put an M here for maximum. The epsilon sub 0 that we used before is not permittivity, even because one was a lowercase and one was an uppercase. Or they're not the same epsilons. So this is what we went through last time. We eventually had that the current was a negative sine function, which is in green right here. My voltage is a cosine function, and so obviously they are not in sync with each other, or not in phase, as is typically said. Because the voltage starts at the maximum value, maximum instantaneous value, because again, the projection onto the horizontal axis is the instantaneous value. As it starts rotating counterclockwise, as phasors are wont to do, it's going to start rotating that way at that angular speed. VCC starts as a negative, starts at the maximum value and then slowly gets lower. I sub C starts out at 0 and then becomes negative. So I sub C is here, V sub C is there. So if you just picture two arrows sort of rotating around. And we ended up with I sub C leads the voltage by 90 degrees or pi over 2 radians. Now, part I did not do last time is, in our simple scenario right here, the maximum voltage across the capacitor is the same as the maximum voltage across the power supply, because I have only two components. If you work through that, so that basically is what I just said, my current is equal to, back over here, that is my maximum current right there, because this is my equation for current. And so I have I sub C is equal to my capacitance times the maximum value of the power supply times whatever my angular frequency is, because maximum value of the power supply, of the voltage of the power supply, and for the capacitor are the same. We can now write it like this. I want to get it into some Ohm's law form. If you recall, V delta V equals IR. I want to get some sort of form of voltage is equal to current times something. And so from that, we end up with my maximum value of the voltage across the capacitor is equal to the current going through the capacitor or onto the capacitor times this 1 over omega C. Again, angular frequency times the capacitance. This 1 over omega C is generally given this designation right here, a capital X sub C, and this is known as the capacitive reactants. That is terminology that is good to know. And given that defined that way, we end up with our Ohm's law form of maximum voltage across the capacitor is equal to the maximum current flowing onto the capacitor and off the capacitor times the capacitive reactance. This would have units of ohms, because I have VI, it better be ohms. So that's basically a recap of what we did on Monday, with the exception of I've now defined this term of capacitive reactance. Slowing down just slightly. Or questions up to there before I talk about inductance? And it looks like you're modeling the screen right there.
I'm processing.
Okay. So similar process we went through before. We have the voltage of the power supply minus the voltage across the inductor is equal to 0. Already taken into account the direction. And so voltage across the inductor is just going to be the maximum value times the cosine, because that's cosine. Plugging in for the voltage across the inductor, and this is something we derived last week, I think, the week before, where we have the inductance times the change in current over the change in time. And there's a little subscript L there. This is the current that is going through the inductor. Dividing by L, we have this coefficient. This will end up, well, we'll get to that in a second. We have the maximum voltage across the power supply over the inductance is times the cosine of omega t is the change in current over the change in time. Ultimately, I want to find a formula for current so that this holds true. Well, we go to what we had done before about the cycle of trig functions. If I have cosine to take the slope, I get negative sine. If I have negative sine to take the slope, I get negative cosine. Negative slope, negative cosine, take the slope, I get sine. Sine, take the slope, I end up back at cosine. So I want some function that when I take the slope, I get cosine.
Sine.
Which is why I have sine written right there. So my current is the sine of omega t times, and then there's this omega that pops out when you do the slope. So if I went backwards, if I took the slope of this, I'd have cosine omega t, and then times whatever, multiplying times the omega, which would cancel out with that, which gets me back to here. So I end up with the current is a sine function. So if in purple here, I've written my voltage across the inductor. In green there, I've done the current. And so you can see, once again, they're out of phase, just like with capacitance, except this is a negative sign and this is a sine. So if we think about, again, two arrows, we got our twister board right here. We got our two arrows that are basically all going to rotate around. Voltage starts at the maximum and then becomes less. Current starts out at 0, so that means it's either pointing down or up. Then, as it rotates around, it becomes positive, so I starts there and then starts rotating around in the counterclockwise direction, so it becomes an instantaneous value. It's positive at a maximum, less so 0, and then so on, basically describing that right there. So, as indicated by this, and again, phasors rotate around counterclockwise at some angular speed of omega. The voltage leads the current. So with capacitors, the current leads the voltage. With inductors, voltage leads the current. It's an I. So for an inductor, voltage leads the current. For capacitor, current leads the voltage.
You are nice, man.
That's right. Trying to get our Ohm's law variation there. I know my maximum current is just this coefficient right there. So I set it equal to it. Solving for VL, because again, Ohm's law, I got some voltage is equal to current times something. So I have voltage is equal to or maximum voltage is equal to maximum current times L omega. And so that is my inductive reactance. XL is equal to omega L. And then we get our Ohm's law version. And that has set the stage for actually doing an analysis. These rules right here are true. No matter how complicated the circuit gets, these are always going to be part of it. And the one other thing, so Ohm's law applies to the maximum values. Kirchhoff's rules apply to the instantaneous values. So incredibly neat, right there. So now what I'd like to do is actually do a problem. Questions to hear?
Do you mind if I get a closer photo of this, just because I don't know if it'll capture on the camera as well? I would really appreciate that. Thank you.
I'm now going to erase pretty much up to the rules that are always true. Questions?
Yeah, sure, sorry. Thank you.
Everyone good? So the lab that you're going to be doing next Wednesday, and I'm hoping only on Wednesday, it'll be what it will be. Is the RC circuit. Actually, I should say RC series circuit, so why don't we start there? I tried to get an RLC circuit, but it's difficult to find an inductor that is the right value so that it either is not overwhelmed or overwhelms the other two components. So the way you solve something like this is, first off, what is going to be the same for everything? If I have a series circuit, what is the same?
Is it the maximum? Is that what we were?
Think back to when we were doing this in chapter 21.
The voltage is changing, so is it the current that stays the same?
Yes,
it
current is the same for everything here. So when I do my phasor, I'm going to start out drawing a current, my current phasor. Now you can draw it anywhere that you actually want. I typically do it somewhere into the first quadrant, and sometimes I'll specify on a problem where to put it. But this would be my current coming out of the power supply, which is the current across the resistor, which is the current on and off the capacitor. This is three phasors all drawn here. Because typically in a phasor diagram, you're drawing the current and the voltage for each component. And because they're all the same, I got three done right there. So the rules. I know that the current phasor is the current is in phase with the voltage for the resistor. So, well, in phase means those arrows are smack dab on top of each other. There's the current for the resistor. There's the voltage for the resistor. It's in phase. I know that the voltage for the capacitor, or that the current across the capacitor leads the voltage across the capacitor by 90 degrees. Well, there's my current for the capacitor, my voltage, supposed to be 90-degree angle there. Now, I don't know how long to make it. This is just sort of sketching it out. We'll figure out lengths later. So this AC circuit can be analyzed well, right now I've got 5 phasors up there. And just imagine this thing is spinning around. What I don't have yet is the voltage of the power supply. That's my last remaining phasor. And I know that the sum of these two, if I'm going from this point to that point, the sum of those two better be the same as that. So my voltage phasor for the power supply is just the sum of these two. And you add them like vectors. They're perpendicular to each other. That's the phasor for the power supply. So if I set up this circuit and I did measurements of the voltage for each of these and the current, I would expect the phase shift of the voltage for the resistor to be the exact same thing as the current. And it comes out pretty darn close in the lab. I will expect the voltage for the resistor and the capacitor to be off by pi/2 because the lab quest is going to give it to you in radians. This, we need to figure out that angle right there, which will probably wait till Monday. Well, not probably, it will wait till Monday. But I would expect the phase of the power supply to be somewhere between these two. And that is the cliffhanger for the weekend.